Okay, hello again to everybody. Welcome to our new webinar. We can start. This new webinar is related to any possible solution to replace PTFE in self-lubricant compounds. As we already know, in the next few years, possible restriction could take place in order to ban all the PFAS substances like PTFE. That's the reason why customer and we are exploring. This new world in order to replace PTFE with other substances without it. It's very difficult, as we will see in the next few slides with the real test that we are going to show you. But we found some solution that can work in some particular cases. Let me first introduce myself. My name is Jacopo Carabelli, and I work in the technical assistance of LATI. And a few words about the kind of webinar. This is not a marketing webinar, but a technical one, because we are going to show you all the results that we obtain in these last 2 years, positive but also negative results. So let's first give a look to the agenda. So we will start to understand why PTFE is so effective from a tribological point of view in thermoplastic compounds, starting from the chemical structure of PTFE, which is the key under the outstanding performances. Then we will see how is it possible to approach a replacement problem like this one. How is it possible to take reference to select correct device in order to understand and test the tribological properties? Then for sure we will give a look on the real test, on the real results, and at the end we will make some conclusion and give some tips in order to go on with other tests and explore maybe other solutions. Before start, I highly recommend to you, if you are particularly interested in this topic, to give a look on our YouTube channel, because we have already faced this kind of problem. We have already talked about tribology science, and in the first webinar who took place in 2022, we talk a lot about the tribological science, and also how is it possible to detect, for example, the wear resistance or the friction coefficient, the behavior of the polymers, and how this behavior change adding fillers or some specific self-lubricant additives. Last year, we talked deeper about the problem of PFAS, so the possible ban of PTFE also, and we made also some proposal already existing in the market to replace it in self-lubricant compounds. As you know, this is the point. The problem is that possible restriction could take place in the next few years due to the fact that all the PFAS substances like PTFE are considered toxic for the human body, but also for the environment. They have an high bio and eco accumulation, and so they are considered dangerous for both the body and the environment. Now the European Commission is making some new evaluation, also thanks to new studies he asked, but also with the help of external entities. And rumors says that probably some restriction can take place, but not before 2029. In any case, we are waiting for an official answer by the European Commission. Let's give a look, as I've already mentioned, about this outstanding substance, the PTFE. What is the secret of PTFE? The secret of PTFE is the chemical structure. The macromolecule of PTFE, the polymeric chains, are really, really long. The molecular weight is really, really high. even if the molecule itself is really simple, only two different elements in the chain, only carbon in the main chain and fluorine in the side groups. And the secret is the covalent bond between carbon and fluorine, which is probably one of the most the strongest bond available in nature, due to the big difference in terms of electronegativity of these two elements. A very strong bond means that you need a lot of energy to break it. That's the reason why PTFE shows a very, very high thermal stability. The melting point of PTFE is over 300 degrees. It's also very high, the chemical inertia is very inert and resistance against, for example, strong acids or strong bases, strong oxidants. So it's widely used also alone, not like an additive, but also as a base resin in very aggressive environment. It also exhibits a very low surface energy. It doesn't like to adhere with any other substances, so it's very difficult, for example, to paint it or to glue it. This is very important because due to the fact that it doesn't like to adhere to a counterpart, it shows a very low friction factor in relative movement against another parts, for example, metal or another plastic part. For the same reason, it exhibits a very high resistance to the adhesive component of the wear. At the other end, the force between this big chain, so the intermolecular forces, are really weak. So the forces between the polymeric chains. That's the reason why, in order to laminate it, you need not a big energy, a big work. So it's easy to shear the molecule, to laminate it. That's the reason why PTFE, it's range, but it exhibits a very low abrasion resistance. In fact, there are many solutions in order to improve it. For example, solution with the synergistic effect between PTFE and aramid fiber. It's just an example. Other properties are the fact that it can be used with any polymeric matrix, from polypropylene to PIC, polyamide, PPS, and so on, without compromising a lot the mechanical and also the thermal properties of the main resin. But what is the mechanism at the basis of the outstanding tribological performances? Just imagine to have a compound, so a base resin, the grain material, with the PTFE, the white bubbles, dispersed inside the matrix, and the relative movement against a metal, for example, the part in orange. The first step is a burning step. So any kind of surfaces are not flat. They have peaks and they have valleys. Through the relative movement of one surface against the other, we have the removal of the surface roughness for sure. Due to the very low intermolecular forces, during this movement, it's very easy to shear the PTFE chains, which fill the roughness, so the valleys of this kind of surfaces. Let's make a zoom on one of these valley filled by PTFE, and you can see that there is the white bubbles with PTFE inside. The second step is the breakage of these very long PTFE molecules in several smaller molecules, smaller chains. So the chain breakage, which leads to the formation of very, very reactive molecules, very reactive radicals. These radicals are then transferred onto the counterpart. So there is a film transmission to the counterpart. So at the end, we will have PTFE on one, but also on the other surfaces of both materials. So we have PTFE who is sliding against PTFE. so with a very highly oriented chains. So a very good situation due to the properties that we mentioned in the previous slide. PTFE works in a very good way, above all for high load and with low speed. And the typical percentage we normally have PTFE in the compounds goes from 5 to 20%. So the secret is this film transmission that we try to obtain also with other polymers, as we can see in the next few slides, to take advantage from it. So to be a good alternative of PTFE, what are the main requirements? For sure, the high chemical inertia, in order to not lower the chemical inertia of the base polymer. Thermal stability, for sure. A good processability, because it's important also to guarantee a good process, a good moldability of the final compounds with good also viscoelastic properties. Not compromise too much the mechanical properties, for sure, at the end, but probably is the most important thing, with an eye to the price. As we already know, one possible solution was one possible candidate already used in the market is a polyolefin, very strange polyolefin. The name is ultra-high molecular weight polyethylene. So it is an high molecular weight polyethylene, a polyolefin. This is the chemical structure. Also in this case, the molecular weight is really high, like also the crystallinity, but the molecule itself is really simple, only 2 elements in the polymeric chain. The density is lower compared to the PTFE, which is higher than 2. In this case, is lower than 1, so very low compared to the PTFE, with an excellent chemical inertia, like all the polyolefins, like polypropylene, polyethylene, and so on. A low melting temperature, around 135 degrees, so 200 degrees lower than PTFE. But another advantage is also the GWP, so the carbon dioxide emission, in order to produce 1 kilogram equivalent of the product, which is really lower compared to the PTFE one. Up to now, what we have already done, and also our competitor did, for sure, we have already analyzed, so we know the behavior, the tribological behavior of the base polymers with some modifiers, elastomers, and so on, with the existing self-lubricant additives in the market. And also we know the behavior adding some reinforcement, some fillers or some fibers like glass fibers and also carbon fibers. We know very well also the synergic effect of different self-lubricant additives available in the market, like, for example, silicone oil, aramid fiber, molybdenum bisulfide, graphite. But for one reason or the other, they cannot be considered equivalent to PTFE, because they can work in with some boundary condition, but not in any kind of condition like the PTFE applications. So what we need to know is explore something else. Try to find other additives, try to find some main fillers to add to replace PTFE, but also explore the synergist world. And that's what we did. We performed this job thanks also to Politecnico of Milan, a university based in Milan. And this study is also a thesis of a student who graduated 2 weeks ago. And this collaboration gives us also the opportunity to have access also of many topics in the literature, many books and so on. And so it was a very good collaboration which helps each other. So let's make the point in order to understand how is it possible to approach this kind of problem. First, we performed a literature studies, thanks to the university, thanks to the help of also our suppliers, in order to find some suitable or possible candidates like main fillers, but also synergists. Then we had also to define some reference point to evaluate the friction and wear. So some material which are the reference to start. Then we had also to define, and it lasted a lot of time, the most suitable condition. And as you can see in the next few slides, there are many conditions, there are many parameters that are possible to set in a tribological device to define the most suitable method to detect the wear resistance, the wear factor, but also the friction coefficient. For sure, at the end of these studies, we had also to analyze all the other properties of the compounds that we produced. So the mechanical, the thermal, also the thermal properties, and also the processability and the reliability. It means the industrialization of this kind of material, in order to understand if it's possible also to push to them. With an eye, as already mentioned, on the price and the marketability of this new proposal. So, for what concern the test, there are many kind of devices available in the market to measure the wear resistance, but also the friction coefficient of polymers. We selected a pin-on-disc method. The tribometer is made by Nanovea, and the pin is made in stainless steel, while the disc is made of plastics, the compounds that we want to analyze, and is put in rotation against the pin. As you can see in this slide, there are many parameters that we can calibrate, but the most important one are for sure the rotational speed, 100 RPM, and also the load, which is 10 Newton. It's also important to notice that we put blown air on the wear site in order to remove all the particles that were created during the test. For what concerns the reference, we started with a material that for LATI is a standard material, so the polyamide 66. So we started to evaluate the performances of an unfilled polyamide 66 in order to fix a reference. And then for sure, we selected also a polyamide 66 plus 20% of PTFE, because the aim of this study was to replace it with other candidates. So we use these two materials as reference. And then for sure, we didn't tested only ultra-high molecular weight polyethylene, but we tested a lot of other additives as main filler. For sure, we tested many different ultra-high molecular weight polyethylene, because there are a lot available in the market, and they are all different for example, what concern the granulometry or the molecular weight distribution or the viscosity, and each one behaves in a different way. So it was really important to analyze the performances of all of them. Then for sure, we tested many others. So for example, we tested ceramic layered structure like metallic sulfate. We tried some polymers in order to take advantage by a possible film transmission, like what happened in the case of PTFE. We also tested recycled composite from a wind turbine, so glass fiber plus thermoset, and also a modified version of LDPE. Then we had a look also on the synergist. And also in this case, we try to find something that from the literature can work, like synergist, with a main filler. So for example, a lot of lattice structure materials like ceramics, like boron nitride or molybdenum disulfide, but also some carbon-based material like carbon nanotubes, which should help to improve the nucleation and so the hardness of the surface of polyamides and other semi-crystalline materials, and also graphite and graphene. So let's give a look on the results. There are not all the tests here that we performed because there were a lot, but we try to summarize the best, the most meaningful results that we obtained. So let's start from a reference. This is the typical plot of a tribological test. So on the y-axis, we have the friction coefficient, which is monitored during the distance traveled during the test. So in the x-axis, we have more or less the duration of the test expressed in meter. What is possible to achieve from this plot is for sure the friction coefficient, and which is for a polyamide 66 more or less 0.56. And it's possible also with the device that we used to detect the wear resistance expressed in cubic millimeters over Newton per meter. And as you can see, after a first peak, the value of the friction coefficient of polyamide 66 tends to a plateau. Polyamide 66 is not one of the worst material in terms of tribological properties because it exhibits a very high crystallinity, and this is very helpful to for the tribological properties. So this is the first reference, but the second reference was for sure the polyamide 66 plus PTFE. So our main reference, the goal to get closer. As you can see on the right table, but also on the curve, the friction coefficient is more or less the half of the polyamide 661, and also the wear resistance, the wear factor, is one magnitude order lower than the polyamide 661. So we had a dramatically improvement of both wear and friction. Let's start to see what we tested. Let's start, for example, with some metallic sulfate that we analyzed. As we can see, the tested material is always in black. For what concerned the metallic sulfate, we faced only two small improvement in the friction coefficient from 0.56 to 0.49. But almost no effect on wear. Then we tried to test other polymers to take advantage from a possible film transmission effect, like for example PPOM, which is a polymer used also as base polymers in injection molding. As you can see, the behavior is really strange. It shows a very unstable curve. It seems that the film creation the film was created just for a while and then was broken and then recreated another time. So it's a very unstable curve. The average of the friction coefficient is lower than the polyamide 66. But for what concerned the wear resistant, we didn't face to any advantages compared to the polyamide 66 unfilled. We tested also PPS because in literature we found some interesting results about the use of PPS as self-lubricant additives in some particular compounds. But also in this case, we didn't face to any improvement of the friction coefficient. While, for example, from a wear factor point of view, we obtain a slightly higher, better results, 1.1 per 10 to -5, so a little bit better than an unfilled polyamide 66, but far from, for sure, the PTFE performances. Then we started to analyze some synergistic effect, for example, between PPS and ultra-high molecular weight polyethylene. And here you can see the results. The aim was to help this kind of lamination of ultra-high molecular weight polyethylene, like what happened for PTFE, in order to favor the film transmission. Small improvements were detected on both wear and friction factor, above all if we compare with the version with only PPS. So it seems that the behavior of these two additives together is better than the material with only PPS. Slightly better in both properties, friction coefficient, but also wear. Then, as I already mentioned, we analyzed also the behavior of some recycled composites. Very interesting also from a sustainable point of view, sustainability point of view. In this case, we tested recycled composites made of glass fiber and also epoxy thermoset. We know from the literature that glass fiber helps to improve the wear resistance, and this is what happened because we lowered a lot the wear factor, for sure. Even if from a friction point of view, the glass fiber played a negative role, and they increased the friction coefficient of the unfilled polyamide 66. So in this case, this material can be good, but only for a wear resistance point of view, not for the friction. Then let's have a look on the very positive results. For example, in this slide, you can see the behavior of a polyamide 66 plus 20% of a special LDPE, so a modified LDPE, in order to improve the tribological performances. As you can see on both pictures, in this case, we faced to a very, very low friction coefficient, even lower than the friction coefficient of PTFE. Below 0.2, and also, but unfortunately, sorry, the wear remains very high, so no advantages from the wear resistance point of view. One drawback of these compounds, as you can imagine, you introduce 20% of a polyolefin, so a low melting point resin, and so the thermal properties, but also the mechanical properties are really worse than the reference. So that's the main reason why this kind of solution cannot be proposed to replace one-to-one a polyamide 66 plus PTFE. So we tried also to halve the percentage of the LDPE in order to check what is first the tribological behavior, and we obtain also in this case very good results in terms of friction coefficient, which is more or less comparable also from a curve point of view with the PTFE, while the wear remain too high. But also in this case, also adding 10% of LDPE, the mechanical and the thermal properties of this kind of compounds are really low compared to a polyamide 66 plus PTFE. Then we started to analyze the well-known additive used in the market, the ultra-high molecular weight polyethylene, C. C stands for the entry level, so the cheaper version. And as you can see, we didn't obtain, in this case, any positive results. No improvement from both friction and wear resistance. But fortunately, not all the ultra-high molecular weight polyethylene behave in the same way, like we will see in the next few slides. But this slide is important also to remember you the synergic effect that we have already discussed. So the fact that taking advantage from both PPS and ultra-high molecular weight polyethylene C-type, we obtain a better results than the use of the single additives. So in this case, the synergic effect was confirmed by the friction coefficient which was very lower compared to the two material with one only PPS and the other one with ultra-high molecular weight polyethylene only. Let's move on and let's see another synergic effect that we analyzed. So the ultra-high molecular weight polyethylene in 5% with 1.5% of multi-wall carbon nanotubes, normally used for electrical conductivity for sure, but in this case also to improve the nucleation power, so improve the hardness and the wear resistance. Unfortunately, we obtain very small improvements on the wear rate, but no advantages from a friction point of view, which remained more or less the same of polyamide 66 unfilled. Now let's have a look on a very good result. So the use of another kind of ultra-high molecular weight polyethylene optimized for tribological properties. As you can see, we obtain in this case, this was a very, very good results, the same values in terms of friction coefficient and wear resistance of PTFE. And as you can see on the curve, is very flat, is very smooth compared also to the PTFE1. So this is a very, very interesting result that we obtained. Then we tried also to halve the percentage of 10% of ultra-high molecular weight polyethylene because due to the fact that it's a polyolefin, it reduces the thermal properties of the base resin. So we tried to halve it in order to check if also with 10% we can reach good results. And the answer was yes. The results was still good because the friction coefficient was quite low, 0.3, and also the wear factor remain with a very good level. So also this compound is very, very interesting. We try to halve again up to 5%, and as you can see, for sure, we faced to a value of friction coefficient which was higher than the first two trials. And also the same for the wear factor. But okay, for sure, also with 5% of this kind of polyethylene, we obtain an improvement compared to the polyamide 66 unfilled. Now let's give a look on the synergic effect between the ultra-high molecular weight polyethylene type A and 1.5% of carbon nanotubes. As you can see, no effect for what concern the friction coefficient, which remain more or less the same of the version with only ultra-high molecular weight polyethylene. But from a wear point of view, we faced to a small improvement, which was good. So this is another possible candidate. But not all the synergists work, because, for example, we repeat the same experiment of the slide before, but changing the carbon nanotubes with boron nitride. And in this case, the boron nitrides seem to damage the tribological improvement provided by the polyethylene. So a higher friction coefficient, but also a higher wear factor. So this was a bad result. So these are, in our opinion, the best candidates that we obtain in the second and in the third column. The first one in the second column was the material with 10% of type A ultra-high molecular weight polyethylene. And the other one is 5% of ultra-high molecular weight polyethylene plus the carbon nanotubes to improve the wear resistance. But as you can see, we have already tested this material from other points of view. We detected also, we measure also all the other properties, and there are some difference with the properties of polyamide 66 plus PTFE. First of all, in the case of polyethylene plus carbon nanotubes, the material is more brittle, so we have a lower unnotched Charpy, but also a lower elongation at yield, so lower impact properties. And as already mentioned, for the compound with 10% of ultra-high molecular weight polyethylene, we face two lower thermal properties, more or less 20 degrees lower for what concerns the V-cut point and also the heat deflection temperature at 0.45 megapascals. So for sure, we obtain very good results in terms of tribological properties, but we need to take care of all the properties at 360 degrees, and for sure in this case we have to face to these lower thermal ones. We also performed some extra tests in order to see if the same additives, which works in a good way for a polyamide 66 plus PTFE, the same advantages can be obtained also with another material, for example, with glass fiber. This is our material, our polyamide 66, LATI 66 20TG20 is our polyamide 66 plus 20% of PTFE and 20% of glass fiber. And we tried to replace all the amount of PTFE with ultra-high molecular weight polyethylene type A. This is the plot, and as you can see, after a starting point, okay, a running step, more or less the friction coefficient, the average of the friction coefficient is comparable to the material with the black one, so the material with PTFE. So also in this case, this kind of additives seem to work in a good way. We made also another experiment, so we tried to replace PTFE in a material that I have already mentioned, the polyamide 66 with 10% of PTFE and 15% of aramid fibers. And we tried different additives in order to replace the 10% of PTFE. The black curve is the reference, so the behavior of PTFE plus aramid fiber. But as you can see, adding LDPE instead of PTFE, we obtain a very fluctuating curve and not a comparable wear resistance, but also with other additives that we tried, for example, the ultra-high molecular weight polyethylene A and the molybdenum bisulfide plus the LDPE, we obtain not comparable results. So in this case, we have not found a solution yet, so we are working on it with other possible candidates. So this slide is very important because if the scenarios are different, probably also we cannot use the same additives for all of them. We need to optimize the formulation, the additives choice, sorry, with the for every different formulation, for every kind of materials. So what are the conclusions of these webinars? The conclusions are that the PTFE offers outstanding properties in all the conditions. The ultra-high molecular weight polyethylene is not comparable to PTFE in all the conditions, but in some conditions can work. We learned that it's possible to replace PTFE with some candidates, but only, for example, to replace the friction behavior or only the wear behavior, not two together for some additives. but we obtain very good results for some kind of ultra molecular weight polyethylene, for example, the one with type A. And there is a word behind the possible synergist choice. In this case, we need to work a lot to find a different solution, to find other synergists and try them in different solutions, because the results of some synergic effect are really, really interesting. For sure, more tests are necessary, because if we change the boundary condition, if we change, for example, the load or the rotational speed, probably also the results can be different. That's the reason why these are comparable results, but at the end, also tribological test on the real part, on the real molded part with the real boundary condition are strongly recommended. That's all. If you have some question, you can write them out in the chat. So let's see if there are some questions. You can write them also now. Otherwise, you can also write an email, and we will try to answer by emails. I have a question I can read. Can the same additives be used for other resin? The answer is yes, but also no, because as you know, the ultra-high molecular weight polyethylene is a low melting point resin, so it can be used, for example, for some resin like polyamide 66, which show a processing temperature around 270, 280. But for high thermal polymers like PPS and PEEK, it's a little bit more complicated to maintain the thermal stability of this kind of filler, so it depends. For this kind of high thermal performance polymers, we are working, and for sure we also found some different additives with respect to the one that we tested for polyamide 66. Another question, are some of these grades available? Yes, some of them can be already available. Some of them are in the industrialization step. So if you are interested to test some of them, you can write to me or to our sales force, and we can provide to you also data, mechanical properties, thermal properties, and so on. So that's all from my point of view, and thanks, and have a nice day. Thank you very much. Bye.